I want to thank you all for coming to our 12th lecture of a series of radio astronomy talks that we've had in the last year and a half. This series was initially supported by George Halburn, the late George Halburn, and then his family continued the support of this series, and we're having basically one lecture per quarter for radio astronomy talks. So we dedicate this series also to the memory of George Halburn, a true friend of our department. I also like to thank the chair of our department, who's also helping us to provide more support for videotaping this series. So if you're interested to look at the series online, we have actually a link on our department, and you can actually listen and watch all lectures that we've had. So today we're pleased to have our distinguished speaker, Dan Werthimer from Berkeley, visiting us today and tomorrow. In fact, I asked him to give 2 more talks. So he's giving 2 more talks tomorrow. But today he's actually giving the formal talk, radio astronomy talk here. Dan is a native of Evanston, and he actually grew up until he was 6 before he moved to California, and has been there in Berkeley for ever since, right? He's currently chief scientist of the Berkeley SETI Research Center, overseeing SETI at Home, the $100 million Berkeley Listen project, and several other SETI programs. He actually really invented the whole SETI at Home project. He directs the Center for Astronomy, Signal Processing, and Electronics Research, and is also associate director of the Berkeley Wireless Research Center. So he has many different hats that he's wearing. He got his degree, his PhD from UC Berkeley in 1988, but before he got his PhD, he was actually associate professor in engineering and physics departments of San Francisco State University. He's been a professor at Beijing Normal University, the University of Saint Charles of Marseille, Yotvus University in Budapest. He's taught in many universities around the globe, in Peru, Egypt, Ghana, Ethiopia, Zimbabwe, Uganda, Kenya, you name it. He likes to travel. So that's what I get from all these different places that he has visited and taught astronomy, I suppose, and computers. Dan has published numerous papers in the field of SETI and radio astronomy instrumentation, and he's co-author of SETI 2020 and editor of Bioastronomy, Molecules, Microbes, and Extraterrestrial Life. One last little detail is that Dan was a homebrew computer club and would give Steve Jobs and Steve Wozniak and also Bill Gates, and everybody in the homebrew club became rich and famous except him, but he is having more fun than the rest of them, I think. Today he's going to talk about, is anybody out there? Radio techniques to search for intelligent life. And lastly, please stay around. We have pizza at the end of the talk. Take it away.
Oh, thank you. Thank you so much. It's great to be back here. I think I may be the youngest student to ever attend this university because my dad was a professor here in the 50s, and he was in the Medill School of Journalism, and he took me to class quite often because my mom was also working. And unfortunately, I didn't learn much journalism at the time, but it's great to be back here. Did you want to talk a little bit about this?
No. It was this was just a picture of George Halburn. You go on.
Okay. Next. So today I want to talk to you about this question: are we alone? Is anybody out there? As you know, the field is called SETI, and I think everybody knows the Drake equation, or most of you know the Drake equation. This is the theoretical approach to calculating the number of civilizations in the galaxy. All you have to do is multiply all these things together. The unfortunate thing is we don't know what any of those numbers are. So the theoretical approach really doesn't work. You actually have to look. So we don't really know how life got started, although people have done experiments to kind of simulate the primordial soup. You might know about the Miller-Urey experiments, where they simulate the early conditions of Earth. You put methane, ammonia, hydrogen, water in a flask. You put in some sparks to simulate lightning. And you don't get gorillas crawling out of this thing, but you do get the basic building blocks of life, the amino acids, things that you and I are made of. So we're beginning to understand how life got started. And the optimists are they're optimistic because life popped up early on Earth, pretty quickly after Earth cooled down, life popped up. Didn't take long for primitive life to get started on this planet. There may even be life in our own solar system. So when I go to elementary schools, I tell the kids about Europa, and I tell them we'd like to see if there's something swimming down in the ocean, but there's a problem that there's 30 miles of ice over the ocean. And I ask the kids, how are we going to get through the ice to see if there's something swimming down there? And the third graders, already there's a difference between the boys and the girls. The boys suggest we get through the ice with bombs and machine guns. The girls are usually a little more clever. They want to melt their way through with mirrors or magnifying glasses or something like that. It's interesting already in the third grade. And then I tell them that, well, we don't actually have to bomb our way through the ice, because if you go to Enceladus, there's cracks in the ice, and there's plumes, and maybe we could fly through the plume and see if there's life. But I'm not going to talk about primitive life. I want to talk to you about advanced life. And as you know, the field is called SETI, the Search for Extraterrestrial Intelligence. And I'm not the first guy to do SETI. 200 years ago, there were great ideas for how to do SETI. Gauss, the mathematician, said that we should get in touch with ET by making large geometric structures on the planet. So he suggested making a right triangle 3, 4, 5 miles on a side, a big square of dirt, big square of wheat, big square of water, and ET would look down with their really good telescopes and see that we knew about the Pythagorean theorem. And that was a clever idea at the time. Unfortunately, it was not funded. And then, also 200 years ago, von Littron suggested that we get in touch with ET by digging a circular ditch 20 miles across and filling this ditch with kerosene, and then using this match, not to scale, to make a bright circle of light. And ET would, have their 30-meter telescope or whatever, and they'd look and see this bright circle of light. And they were going to turn the fire on and off and send Morse code and flash it on and off. And it met with a similar fate. And then Charles Crow, this all 200 years ago, suggested we get in touch with the Martians by using large mirrors to reflect the sunlight to the Martians. Actually, several mirrors, one where he lived in Paris, and the others to outline, Ursa Major, Big Dipper. And the Martians would see these bright lights on Earth. And I think you can guess what happened with that project. So the first funded project was to send pornography into space. So this was a plaque on the Pioneer 10 spacecraft, left the Earth in the 70s, in the early 70s. These two were very controversial. And originally they were holding hands. Some people wanted to put clothing on them. NASA said they can't hold hands because ET will think that it's one creature instead of two, so they're not holding hands anymore. Some of the lines were removed from the genitalia. So anyway, and on this thing, on the plaque, you can see the Sun and Mercury and Venus, and here's the spacecraft leaving the Earth. And these are directions to pulsars with the timing, the periods of the pulsars. So ET will know exactly where we live so they can come and eat us. Anyway, that was the first funded project. And then another thing we've been doing besides sending spacecraft out with plaques on them, as you know, we've been sending out television and radio and radar signals now since the 40s. This is a plot of television signal power leaving the Earth as a function of time, 1940, 1950. And this log axis, so you can see we're getting brighter and brighter. We're growing exponentially. And at radio frequencies, at television frequencies, the Earth is quite a bit brighter than the Sun. The Sun doesn't put out much power at TV frequency. So we are very easy to see if you're an extraterrestrial and you tune down to TV or radar frequencies or FM radio. Anything above about 20 megahertz gets through the ionosphere and goes out into space. And so our early shows like Ed Sullivan and I Love Lucy have gone past about 10,000 stars. And the nearby stars have seen The Simpsons. And Earthlings have even sent messages on purpose. You might know about this one sent from the Arecibo telescope in 1973. A lot of people think that pictures are a good way to communicate with ET. And this was a sequence of 1,679 bits. And if ET counts up the bits, 1,679, they will hopefully notice that 1,699 is a product of two prime numbers, 23 by 73. And so they might say, oh, it must be a two-dimensional image that's 23 across and 73 down, or they might try it the other way, 73 across and 23 down, but if they do it one way, you get this picture. Not in color, you just get a black and white picture. And there's the solar system with the Earth, there's the Sun and the Mercury and Venus, and the Earth is tipped toward the person. This is the height of the person in wavelengths that the message was sent. This is the Arecibo telescope. This is the diameter of the telescope. The binary numbers indicate the diameter of the telescope in wavelengths. DNA, some amino acids, and some binary numbers. So we're looking for those signals. Either an artifact that wasn't intentionally transmitted by their civilization, much like our TV and radio and radar leaves our planet. We didn't intend for that to leak our planet. Or, if we're very lucky, although I'd kind of doubt it, some kind of deliberate signal that they intentionally sent for the purpose of interstellar communication. If they do that, they'll probably make it easy for us to decode the message. It'll be maybe, we call it anti-cryptographic, a lot of pictures and language lessons. If we find something that's an artifact of their technology that really wasn't meant for us, their GPS or something like that, my guess is we'll never learn much about them. We're not going to be able to figure out what the content of that thing is, but we'll know they're out there. But if it's a deliberate signal, maybe they'll tell us how to get on the galactic internet, and we could, get in contact with civilizations billions of years ahead of us. Some people call SETI the archaeology of the future, because it's going to be very hard to find a civilization that's just discovered radio the way we have, or just discovered lasers. It's much more likely if we ever find another civilization, they'll be a billion years or a few billion years ahead of us. I'm not the first guy to do SETI. The early radio pioneers, Tesla and Marconi, 100 years ago, both thought that this would be a good idea, and they both went out looking for ET, and both of them thought that they found radio signals from ET. They didn't realize it at the time, but they were listening to distant lightning bolts, and they heard these what we now call whistlers. And when lightning thousands of miles away emits radio waves and light waves, the radio waves bounce up and down off the ionosphere and Earth and eventually get to your radio set. And there's a dispersion as it goes through the ionosphere. The low frequencies get delayed more than the high frequencies. We see this in radio astronomy too. When a signal comes from a pulsar or a fast radio burst, the dispersion, you get this where the low frequencies arrive later than the high frequencies. It tells you something about the interstellar medium. So anyway, they thought it was ET. It wasn't. They didn't know about distant lightning bouncing off the ionosphere. There were other searches in the 20s. The Navy, Mars was very close to the Earth, and the Navy said, everybody turn off your transmitters, and they listened for radio signals from the Martians. So SETI's been around for a while. Of course, so I've been doing SETI since 1974, roughly. And we have a project at Berkeley. We call it Berkeley SETI Research Center. And we collaborate with a lot of different universities and observatories. There are about 20 of us. About half of the people that work in our group are students, undergraduates and graduate students. And they are students from engineering department, because it's a high-tech kind of thing with a lot of computing. And we build a lot of electronics, signal processing hardware, which I'll briefly mention. And then we have students from physics and students from astronomy all working together. And we have funding we just got funding from the Breakthrough Prize Foundation. That was their first funded science project. And traditionally we've been funded by National Science Foundation and NASA and individuals around the world. And some companies that help us out, they donate the hardware, electronics, chips, and computers. And we have several different experiments in the radio and some experiments at optical frequencies looking for lasers or infrared frequencies. And I'll tell you a little bit about some of the experiments that we're doing. But basically, this is a search for technology. We're looking for lasers or radio or radar signals, either accidental or deliberate. And we have telescopes. We have, I think, 7 different telescopes we use now. Optical telescopes, infrared. We have kind of centimeter wavelength telescopes, and we also have meter wavelength telescopes that we're using. And we're trying to kind of look at all the different bands that get through the atmosphere. But we can't really look at the whole electromagnetic spectrum. Right now, we're just kind of learning how to do SETI, and we're just getting in the game. But I'm optimistic in the long run. The technology is growing so fast that eventually we'll be able to do a thorough search of the electromagnetic spectrum. But right now, we can just cover little bits of it. Our very first project was funded by NASA, and NASA requires that you use acronyms. So SERENDIP is a search for extraterrestrial radio emissions from nearby developed intelligent populations. And this was the very first telescope that we used. This is an 85-foot telescope. We used this in the 70s. And this is at Hat Creek Observatory, which is in Northern California near Mount Lassen. And while we were using this to look for ET, to look for radio signals from ET, this is what happened to that telescope. So this is the dish that used to be up here on the pedestal here. So we said, okay, we can't use that telescope anymore. So then we moved to this telescope in Greenbank, West Virginia. This is 300 feet across. And while we were using this telescope to look for ET, this is what happened to that telescope. And you might ask, well, how did that happen? And there are various theories, but this is from the World Weekly News. Zapped by hostile space aliens. The aliens did not want to discover, and they did not want us to discover their location and what they were up to, and they zapped the telescope. So we were interested in this theory, so we wanted to test it. And so we went to this telescope. And so I think most of you know this is the Arecibo telescope. This is 300 meters across, 1,000 feet. So far, the aliens have not zapped this telescope. It holds 10 billion bowls of cornflakes. And we figured out a way to use this telescope at the same time that other astronomers are using it. For those of you astronomers, you know that big telescopes, it's hard to get time on telescopes. You apply, you're lucky if you get a day or two a year. Everybody wants to use the biggest telescope. So we wrote this proposal that said we just want to attach our instrument, no matter where anybody points it, we're going to look for ET, whether they're studying the galaxy or studying pulsar or something. So we're running, as we speak, we're always collecting data. So that's called, we used to call it parasitic SETI, but now we call it, parasitic kind of has a bad connotation, so now we call it piggyback SETI or commensal SETI. Commensal is a biology term, two creatures eating out of the same dish. So anyway, we're running all around the clock. So we get a huge amount of data, a huge amount of telescope time. The disadvantage is that we don't get to point the telescope because it's not our telescope to point wherever we want. But we don't know where to look anyway, so it works out pretty well. And a lot of astronomers are doing sky surveys. They're just doing raster scans of the sky, looking for fast radio bursts or pulsars or mapping the galaxy in hydrogen or something like that. So it actually works out pretty well, this kind of commensal approach. I mentioned that we got this new project funded by the Breakthrough Prize Foundation. It's their first science project. It's called LISTEN, and it's huge. We struck gold kind of by accident. They intend to give us we just started this year, last year. They intend to give $100 million over 10 years, and the guy that gave us the money said, Dan, are you going to find anything in 10 years? I said, probably not. And he said, well, then I'll give you another $100 million. So we'll see what happens. So anyway, we're starting with 2 radio telescopes, Greenbank and Parkes. I'll show you pictures in a second. And Lick Observatory looking for laser signals. This is an observatory in California, not far from where I work. And we plan to look at 1 million stars, although we're not there yet, and 1,000 galaxies. And we're also going to do a sky survey and a galactic plane survey. And we got some very fancy new instrumentation. And we'll also be using our SETI at Home volunteers to analyze parts of the LISTEN data. And I'll tell you more about SETI at Home. All of our projects are open source. The data is open source. The hardware is open source. The software, everything we build is open source. And some of that might be useful for some of you, especially if you're doing radio astronomy. So these are the telescopes we're starting with. This optical observatory called the Automatic Planet Finder turns out has a very good spectrometer. So you can, it's in a shell spectrometer, very high resolution. So you can look for narrow band laser signals. And we're also using Greenbank, and we're using this Parkes telescope. This is in the northern hemisphere in West Virginia, and the Parkes telescope in Australia. As I think if you're an astronomer, you know a lot of really interesting stuff is down in the south, the center of the galaxy and things. So those are the 3 telescopes we're starting with. We just launched the Parkes telescope last month. Greenbank and these we launched last year. And we're hoping to branch out and use even more telescopes. We're starting to talk to people in South Africa about using the Meerkat telescope, which will eventually turn into the Square Kilometer Array. And I mentioned we're hoping to do 1 million stars. There's a lot more than we've done before. Before SETI, people looked at about 1,000 stars. And also galaxies, which are much further away, but we don't know what the luminosity function of extraterrestrial transmitters is. There could be some very bright, powerful civilizations out there. If you're an astronomer, you know the brightest stars are not the nearest stars, because there are some stars that are extremely bright. So that could be the case for extraterrestrials. So we're going to look at nearby stars, stars that are kind of similar to the sun, stars with planets going around. And by the way, there's a big announcement. I think right now there's a big announcement from NASA. Does anybody know about that?
This came out in the press.
Oh, it's come out?
Yeah, it just came out.
What did they announce?
7 planets around TRAPPIST-1, terrestrial planets all in a really compact orbit.
And they're claiming some of them are Earth-like?
They claim they're all terrestrial and that 3 of them or so may be conditions for liquid water.
Yeah.
So they went
So
for 3.
Mike, are they Earth-like or super Earth?
They're, I believe, all smaller terrestrial planets, so Earth-like in that sense. But that's just from the press release, so I don't really know.
I think that just came out. You must be right on the news, or ignoring my lecture and looking at your cell phone. By the way, if you are just following the news, because it is kind of a cool announcement, I do have a summary slide. So just wait, and I'll alert you. It's fine. Maybe at the end you can tell us what else you've learned about the.
It's live tweeting your lecture.
Right. So we thought we would just at the start we'd look at all the different kinds of stars in the main sequence, giant stars. Traditionally, people have looked at these stars that are like our sun, kind of FGK stars. But now, as astronomers learn more and more about where you could have life, it looks like you can have life almost anywhere. And even M stars, little dinky M stars, where we thought you could never have life, are now looking interesting. So we're actually surveying, at least in the beginning, we've selected our first 1,000 stars are going to be all different kind of spectral types and different kinds of stars. We've got some new technology that's, I think, is very cool. I'm a kind of technology engineer. I'm a nerd. I like to build stuff. And we use a lot of these FPGA and high-speed analog digital converters. And I might talk a little bit more about that tomorrow in the radio astronomy class. If you're interested, we'll talk about some of the new instrumentation. But basically, a lot of what you want to do in SETI is you don't know what channel ET might be broadcasting on. So you want to look at a very wide bandwidth as much as you can and divide it up into billions of spectral channels. And our new thing has got about 100 billion spectral channels that we go through. So a lot of SETI is kind of having a lot of computing power, a lot of digital signal processing to do that. And I'll talk a little bit more about that. This is data from the optical SETI project looking for narrowband laser signals. So you look for a laser is extremely narrow. Maybe that could be a laser. So we use very high resolution shell spectrometers to do this. And what you look for is kind of a signal that's not thermally broadened, to just look for something that matches the point spread function of the instrument. Natural lines are thermally broadened. They're much broader than a laser signal. So we look for that kind of thing. And occasionally you find stuff, but it turns out to be a cosmic ray going through the CCD of the spectrometer. And you could tell it's a cosmic ray because it's got a little energy that's off of the where you'd expect you'd expect energy from the diffraction grating to only fall kind of along, and you'd expect it to be vertical. And so we can tell because it kind of comes in at an angle, and there's energy off where the grating would deposit light. So you can usually sort that out. Although we have a lot of these things to go through, so we're trying machine learning algorithms to try to figure out which are cosmic rays and which might be potential signals from ET. In the radio, we have this huge problem at very high data rates. So if you analyze a 10 gigahertz bandwidth from a radio telescope, it turns out to be a few hundred megabits per second. And so we feed that into these things called field programmable gate arrays, which are very good at computing but very hard to program. And we work hard to make it easier to program those things. And then we feed that into a bank of these things called GPUs. You probably know graphics processor units that are invented by Silicon Valley to make games look more realistic. They're high-speed supercomputer boards that the kids buy to make it look really bloody and gross. But we can use those things to do fast Fourier transforms, basically, and do spectral analysis and do other kinds of computing. But we can't record all that data. It turns out that's just like way too much to record. We have a few petabytes of storage, but even so, we can't save all that data. So this might be interesting to some of you. The data that we're saving, so we can't record this kind of raw voltages at a few hundred gigabits per second. So we save some of the interesting data, the raw data, and then we save some of it for SETI at home. And then we compress it into high spectral resolution data, which will be good for people studying galactic structure, making maps of hydrogen or OH. And then we also, this has kind of poor time resolution but high spectral resolution. But there are some people that are interested in transients, pulsars, fast radio bursts. These are sort of microsecond to millisecond events on the sky. So we also record what we call high time cadence spectra. This is every 100 microseconds we record a spectrum. But the problem with that is we can't record high resolution spectra. That's too much data. But that's okay if you're a pulsar guy or a fast radio burst guy. You don't need a lot of spectral resolution, but you do want very high time resolution. So we record actually there's an intermediate kind of data type that's sort of medium spectral resolution, medium time resolution. All that data is being made available publicly. If you're an FRB guy or pulsar guy or a hydrogen mapper, we might have data that might be interesting for you. So I mentioned the data is public access. There's a website. The software is on GitHub. There's some tutorials about little software examples about how to read the data in the file format and so on, and example things you can do with the data set. And there are example data sets that we've got some fake signals in there. We looked at Voyager 1, and you can see a little signal in there. And if you can find the signal, then you know you're analyzing the data correctly. So this is the simplest kind of signal we look for. It's just some strong signal at some frequency. So we want to do very high spectral resolution. You notice that there's millions of spectral channels here, and here's something strong at some frequency. That's the simplest thing to look for. Just calculate a power spectrum. And you want to do all these channels at once. You don't want to tune your radio one channel at a time. You want to build something that can look at billions of channels simultaneously. And I wish I could tell you that was ET, but it's not. It's a satellite going over the telescope. It's a big problem in SETI that we're looking for extraterrestrial radio signals, but what we find are terrestrial, human-made radio signals, and it's getting worse and worse. And that's why we're working with South Africa, because South Africa's got a big desert where nobody lives. It's too hot. It's hot and dry, and so it's a very radio quiet place. But even so, there's a lot of radio frequency interference, RFI, anywhere on the planet. And eventually we might have to go to the backside of the moon and put a telescope there where the moon would shield us from all the radio pollution. That'll be very expensive. So this might be a kind of unique window in Earthling's history where we can do radio astronomy from Earth's surface, where it's not too expensive to build these things. But eventually all the bands are getting filled up. It's getting harder and harder to do radio astronomy from the ground. So that's the simplest kind of signal. And what we've been doing at some telescopes is we do what's called beam switching. You look at a star you're interested in, then you go to another star, then you go back, and you go back and forth. And because of this radio frequency thing, what you want to do, what you expect is if there's a interference, it might be on all the time. So no matter where you're pointing, you kind of see it, and then you know it's interference. If it's here and it's there on the sky, you know it's interference. So what we do is we look on the source and then off the source and then on and off on. We typically do that 3 or 4 times, and then we look for a signal that's in all the on positions, right, when you're pointing at the same place, but none of the off positions. And that's one way to exclude interference, but it takes twice as much telescope time because you got to do this. You got to go back and forth 3 or 4 times to get some confidence that you're only finding it in one place in the sky. So another thing we wanted to do was look for drifting signals. So these are signals that are changing in frequency, or that kind of thing. The reason that could happen is if there's an extraterrestrial transmitter on an accelerating platform, if their planet's spinning around or going around its star, then you would expect to see some acceleration, a Doppler shift. So we want to look for these drifting signals, which you can, I think, easily see in this thing, but we have about 100 million of these things to look at every second. So it takes like 100 million eyeballs or maybe a lot of computing power to find these kind of drifting signals. You don't know the slope. You don't know where in frequency, and you don't know the slope because you don't know the acceleration parameters of their planet. And we also want to look for pulsing signals, a bip, 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 which here I've circled them, so it's pretty easy for you to see. But if I remove the circles, it's actually hard for you to find these patterns. So we need a lot of computing power to look for those kind of things. And then we want to look for other kinds of signals, broadband emissions, some kind of modulation. And so we built this thing that I think a lot of you are familiar with called SETI at Home, where we wanted a lot of computing power to look for this kind of rich variety of signals. You need a lot of computing power. And so what we do is we take the data from Arecibo, we record it at this thing called the National Energy Supercomputing Center, where we have a few petabytes there. And then we break the data up into little pieces, so everybody gets a different part of the sky or different part of the frequency band. We break it up into billions of little pieces, and then we send the data out to the volunteers, the SETI at Home volunteers, to analyze with their home computer. It's a screensaver program. There's what it looks like when it pops up on your computer. This little video of the thing. So the way it works is anybody here ever participated in SETI at Home? There's one, two. Okay, great. So you guys know what I'm talking about. So the way it works, thank you, by the way. The way it works is you download this free program, and you install it in your laptop or your desktop or whatever, Mac, PC. And now it runs on some cell phones if you have an Android cell phone. Anyway, so then when you go off for a cup of coffee, it pops up like any other screensaver, but instead of just putting up pretty pictures on your screen, it's actually going through the data from Arecibo or Green Bank or eventually Parks. And then it does Fourier transforms, it does spectral analysis, it looks for pulses, it looks for all kinds of different signals. And that might take a few days to do that. And it reminds you what your name is, and it reminds you the part of the sky you're looking at, the right ascension, declination, the frequency band. And then if it finds something interesting, it kind of displays it. And then when it's all finished, after a few days, it will send the results of the data analysis back to our server at Berkeley, where the results are then stored on a database, and we'll go through it. The most interesting signals, things that repeat or near an exoplanet, or things that get our attention. We figure out what's interference. And what are the most interesting candidates. And your name is attached to that data. So if you find ET, you get the Nobel Prize, maybe. This is a little animation of the data coming out from Berkeley, going to volunteers around the world. The data coming out are the yellow dots, and then when they're done analyzing it, they send the results back. That's the blue stuff coming back from volunteers around the world. So I mentioned that you might get the Nobel Prize, but there is a catch. The Nobel Prize is about $1.5 million, and there are about 8 million people who've downloaded the SETI at Home screensaver. So if you have to share the Nobel Prize with all those people, you're not going to get rich. You get maybe 20 cents or something like that. But anyway, the volunteers have donated 3 million years of computing time. They donate about 1,000 years per day. That means if we just had a single computer, it would take us 1,000 years to do what the volunteers do in one day. So we're very grateful to the people here who are running it. And I hope after this lecture, all of you will download it and help us hunt for ET. If you want to participate in SETI at Home, just Google SETI and you'll find it pretty quickly, and you can download it. If you put it on your phone, it kind of sucks the battery way down. The default setting is it will only run when the phone is charging. I recommend you leave that setting, because if you run it while you're carrying it around, the battery kind of goes down pretty fast. So you don't have to do this, but if you join SETI at Home, if you want, you can also join a team, and there's primary teams, secondary, junior colleges, university. I don't know if there's a Northwestern team, but if there isn't, you can make one. There are thousands of teams that you can join. You don't have to join a team. You can just participate as an individual. But this competition has led to some kind of good behavior, maybe bad behavior, but these teams compete with each other. IBM has donated 3,000 years of computing time. And then there are individuals that compete with each other, and some of them build big clusters in their basements. And you can go to this website, setifarm.org, and you can see thousands of people who built these clusters. They're all men, as far as I can figure out, and I think they're all single, but I'm not sure. And this guy's posing with his SETI at Home cluster, and this guy's posing with his cluster with these bolt cutters. I don't know why. We haven't found ET, but one of the things we're happy about is that it's getting kids involved in a big science question, are we alone? And this question, are we alone, as you know, the kids, it touches on so many different aspects of science, of all the different factors of the Drake equation. How does life get started? They learn a little bit about biology and evolution. They learn some chemistry, and then they learn about planets and astronomy, and how about and then you can tie it into physics, and you can tie it into computing. So this question touches on so many different aspects. It's a great hook to get kids interested in science. So we developed some curriculum with the Lawrence Hall of Science that a lot of kids use around the world. And there are a lot of children either using it alone or as part of their curriculum where they kind of participate in a global science project. And that kind of led us to think about, could we use our software that we developed for SETI at home could it be useful for other scientific supercomputing projects? This idea of distributed computing, or we call it edge resource aggregation. It turns out most of the computing power is not in big supercomputers. It's mostly at the edges of the internet. It's the stuff that you and I own, little computers. If you add all that up, it's way more computing power than in the kind of centralized machines. So we developed this software so you could participate in lots of different science projects. It's open source software called BOINC. And now there are about 100 different projects that use our software. So now you can allocate how you want your spare cycles of your computer to be used. You can say you want 30% of your spare cycles to go for SETI and 20% for malaria drug research, and there's cancer drug research, and there's HIV drugs, there's climate change, global warming research, and there's all these different projects that you can choose from. This is global warming, climate prediction. This is a gravity wave, Einstein at home. This is Astropulse, looking for primordial black holes, radio pulses from primordial black holes, and fast radio bursts. This is a protein folding project. Anyway, you can pick the projects that you're most interested in. That's volunteer computing or distributed computing. We call it the democratization of scientific supercomputing. It used to be you had to have a lot of money or kind of good connections to get time on a supercomputer. But if you've got a cool project, maybe you can get volunteers to help you. Then we kind of branched out. We tried to think of things that computers are not very good at. Our very first project, our first citizen science project was called Stardust at Home. So we worked with NASA and the University of Washington. We built this thing called Stardust, and we sent it out to scoop up dust. It went through a comet's tail, and then it also picked up some of the early dust that was around when the solar system was forming. It went out near Jupiter, and we collect some of that primordial dust that was left over after the planets formed out of that dust. And it was a sample return mission. It came back, landed in Utah on a parachute, and the samples are in our lab in Berkeley. And this is the way you collect these samples is something called aerogel, which is a very low density glass foam, and they're little microscopic particles traveling at 30 kilometers a second. And that's kind of hard to collect because usually if they hit something, they smash into a zillion pieces. But this aerogel is very low density, and they smash into the aerogel, but instead of blasting into 1,000 pieces, they come to rest somewhere in that foam. But they're little microscopic things, and we have huge chunks of this aerogel. We had to find these little particles in there. And we thought when we launched this thing, we'd need 1,000 students looking through 1,000 microscopes to find the little microscopic particles of dust. And instead what we did is we put the aerogel on an automatic microscope. This got X, Y, and Z under computer control. And we took, I think, about 50 million photographs of different places. And now, so if you want to help us find the particles, you download this virtual microscope. You sign up for the Stardust at Home project. You take some training courses to see what the particles look like and what the false alarms look like, and then you can start using your virtual microscope to go through all these photographs that were taken at Berkeley. And if you find a particle, you get your name on a Nature paper. And it's a quick way to get your name on a Nature paper or a science paper. And the volunteers, there are about 100,000 of them, have found particles we probably never would have found if we just had students looking through microscopes. There's a big problem looking through a microscope for hours and hours. You get this fatigue and you miss things. But the volunteers found a lot of good things, and they help us understand how these dust particles stick together to form the planets and what they're made of. So that was our first citizen science project. Now there are a lot of citizen science projects. Some use our software, some don't. But that was one of the early citizen science projects of things that your brain and your eyes are better at than computers. Let me get back to SETI for a second. One of the new things we're doing is called interplanetary eavesdropping. The idea of interplanetary eavesdropping is that if there is life evolving on an exoplanet system with multiple planets, like the one we heard about with 7 planets, did you say? So this just shows you 2, but suppose life starts on one, then they send probes or other species to a different planet. These 2 planets are going to be maybe communicating back and forth with lasers or radio or something like that. And now, because of Kepler, we know exactly where these planets are in their orbits, what their phase is, and then we can predict when these 2 planets are lined up with Earth, and we can schedule our observations. So if there's radio or laser traffic going back and forth between 2 exoplanets, we can maybe intercept it. This is a new thing that we couldn't have done without Kepler a few years ago. Kepler found all these. Is the new result from Kepler probably?
Trappist.
Oh, okay. Yeah. So that's a new thing that we're doing to do kind of eavesdropping. Another thing we're doing is I mentioned looking for laser signals. This is at Lick Observatory. This is Frank Drake, one of the early pioneers. Shelley Wright at UC San Diego was a student of mine. And Rem Stone, who was the director, and that was me in my younger days. And we've also got a project at Keck looking for laser signals. There's a new paper about that. And we've also got some infrared stuff that we're doing. There's an interferometer that we use this is at 10 microns, looking for. We think infrared might be a good way to communicate because infrared, if you're an astronomer, you know, goes through the dust. Optical light doesn't go through the dust, so you can't see the center of the galaxy at visible light. But you can see it at infrared, which gets through the dust. And so for long-range communication in the plane of the galaxy, we think infrared might be a good way. And so we've got this infrared interferometer that wasn't built for SETI. The guy who built it is Charlie Towns, who invented the laser, got a Nobel Prize. And his office was right next to mine, and he kept saying, Dan, you should look for laser signals. I said, Charlie, their lasers are little dinky things like this. They were at the time. And then there's no way that ET could use these little milliwatt things to communicate. But Charlie was right. Now there's sort of, megajoule lasers, incredibly powerful things that could communicate across the galaxy. And so we started looking for them. Charlie died a couple years ago at 99.52. We round up to 100. And kind of amazing, when he was 99, he was coming into the office every day and talking about SETI and lasers, and was kind of brilliant all the way up until he died. He was a lot of fun to work with. Okay, well, we have not found ET, but we've made some discoveries along the way, and I'm a little uncomfortable arguing that you should fund SETI because of the spin-offs. It's like NASA saying, give us money because we invented Velcro and Tang, but we haven't found ET, so that's all I can think of. So one of the things I mentioned was a lot of the instruments that we developed, which have all this signal processing electronics and the fancy kind of capabilities, a lot of computing capabilities, got used by a lot of different radio astronomers, for the pulsar people and the fast radio burst people, and all kinds of anybody who wants to build a spectrometer or a beamformer or a spectral imager or something like that needs a lot of computing power. And so our instruments got used for a lot of different things. And we formed this collaboration called CASPR, which is Collaboration for Radio Astronomy Signal Processing and Electronics Research, and there are about 1,000 of us that work together on building the new next generation instrumentation for radio telescopes. And that's led to a lot of discoveries. So one of the discoveries that was made with instruments that we designed for SETI was a planet made out of solid diamond. My wife is very interested in that. And Farad and I were talking about this. The instruments that we designed for SETI were used to make the very first images of the black hole, the center of the galaxy. This is using millimeter wavelengths interferometry with telescopes at different places on the world. We use SETI instruments to record all that data and to correlate all that data to make the first images. And then what else? They've been used to find the most massive pulsar. There's a couple solar masses. And that led to people that are studying solid state physics to rule out a whole bunch of equations of state. And the kind of theorists went crazy, and they quickly came up with new theories, though, to explain how you could make a 2 solar mass neutron star. It's been used mostly in radio astronomy, and it's led to a lot of discoveries, these SETI instruments. But it's also starting to get used in other fields. Some medical people used our instrumentation to read out data from a brain they put a little chip in there and it broadcast data, and we were able to receive it and decode what was coming out of the electrodes. And eventually we hope to use it for controlling prosthetic arms. So with a little implant and reading out the radio waves from the implant to control prosthetic arm. But we're not there yet. Well, let me get back to SETI for a little bit. I want to tell you a little bit about what we're planning in the long run. So we want to go to bigger telescopes. We want to have bigger instruments. So the Chinese are building something that's even bigger than Arecibo. Arecibo is 300 meters. This is 500 meters. It's made out of thousands of these little panels. And it's got lots of actuators that move the panels around. Here you can see what the size of this thing compared to Arecibo and the Green Bank telescope we use and the Statue of Liberty there. So it's a big telescope. It's just getting going now. It's not ready to do science yet, but we're going to do a big survey that we will start in a couple years where we're going to survey the sky and do 5 things simultaneously. We'll look for new pulsars, which can be good for measuring gravitational waves. We'll map the hydrogen in the galaxy and other galaxies, which is good for studying galactic structure. We're going to be looking for fast radio bursts. I just came from a fast radio burst conference in Aspen last week. It's a very exciting field, a whole new field of astronomy. We think they're going to be very good cosmological probes. They come from pretty high redshifts, and maybe you can measure the baryon density of the universe. That's an exciting new field, so we want to find more of those and figure out what's going on there. And then, of course, we're going to be doing SETI and a little SETI at home. And so we're going to try to do a bunch of things while we're surveying the sky at this new telescope. But that won't start for about a year, although we're trying to get it going this year. And then another thing that we're interested in is how to build telescopes out of lots of little telescopes. So this is a thing that we're building in South Africa, and it's made of little dishes that are 14 meters across. We don't have 352 of them now. We have 37 of them now, and we're just getting going on that. But next year we hope to have 352 of them. And that is being used as an epic reionization project to learn how the first stars and galaxies formed at a redshift of 10, maybe a redshift of 20. And so we're just getting going on that experiment, but we're also going to do a fast radio burst and SETI experiment while we're trying to figure out this epic reionization. And eventually we hope to get on the Square Kilometre Array, which is a project being built in South Africa and in Australia, and we're starting to work with them on their prototype experiments. And this will be a thing made out of thousands of dishes, maybe 4,000 dishes. And it's a big international project. A lot of countries involved, but not the United States. We're also learning how to look at many places on the sky at once. We've been studying these phased array feeds, which allow, optical astronomers have had, for years, they've had millions of pixels, but radio astronomers typically one beam at a time. It's kind of painful. But now this thing allows us to look at maybe 64 beams, and maybe we'll get up to 1,000. But we're a little jealous of the optical astronomers. We're also looking at these new wideband feeds that can cover a big chunk of the spectrum from 1 to 15 gigahertz. That's kind of new. Typically, you can cover an octave or so if you're lucky, but this will cover several octaves at once. And we're looking at kind of whole new technologies that will allow us to look at the whole sky at once. This is a thing being built in the Netherlands. It takes a lot of computing power to make all the different beams in the sky. You need to digitize data from 20,000 different things. But that computing power is coming down so fast. We think this might be the future of radio astronomy. It'll be made out of lots of little dipoles, which you look at the whole sky and you can form beams everywhere in the sky. So we're looking at that, but that's a decade or more away. We've also been talking to the people that do Cherenkov studies of the atmosphere, looking for gamma rays. But they have huge telescopes. They have several 12-meter telescopes now, and they're talking about 23-meter telescopes. And it turns out the instrumentation that they deploy looking for this Cherenkov radiation can be very adapted quickly to look for laser pulses. So we've been talking to them. One of the things I'm excited about in SETI is that I mentioned that right now we're just kind of learning how to do this. We're an emerging civilization. We're getting in the game. And we can't cover big chunks of the spectrum. So when I first started, I built a thing that could look at 100 channels, and I was very proud of this thing, 100 channels, because before that, people just looked at one channel at a time. And then I built a thing with 65,000, then 4 million channels, and now it's 5 billion channels. That's not because I'm getting smarter, it's because Silicon Valley just cranks out this stuff. and we take advantage of it. So that's a factor of 2 every year. So I think we've got a long way to go, but if this trend keeps up, I think eventually Earthlings will be able to do more thorough searches and see if there are radio signals. This is computing power as a function of time, 1960, 1970. Right now, computers are as smart as a lizard or a guppy, but if this exponential growth keeps going, computers will be as smart as humans at 2030 or 2040. That could be very good for SETI, maybe not so good for humanity. The singularity. Watch out. So, and then we don't know how to do this now, but maybe in 100 years you can use the sun as a gravitational lens. This is something Einstein talked about, but if you could do that, if you could put a camera, it's way out beyond Pluto, you put a camera out there, you could read license plates on an extrasolar planet. Maybe these 7 things that NASA announced today. That'd be kind of fun, if there are license plates on extrasolar planets. Let's see, if you have been asleep or looking at this newscast from NASA, this is the summary slide I was talking about. This is the only slide you have to remember. No ET so far. We're still working on it. But it's actually not my last slide. I got 3 more slides. So I wanted to kind of acknowledge all the help that we get from the SETI home volunteers. So they form one of the biggest supercomputers on the planet, made the search way more sensitive and more powerful than anything we could have done with our own computers. We used to use the computers in the building, when people went home, we'd use everybody's computer, and then we use computers in other people's building on campus. But now we're using computers in 226 countries, and we're very grateful. And the volunteers, not only have they made it a very powerful and sensitive search, but they also help us in lots of different ways. I mentioned it's an open source project, and they help us write the code and get the bugs out of the code and port it to new platforms and speed it up. And some of them send money. That's very good for the students. That keeps the students going. And some of them have composed music about SETI and literature. And some of them have composed poems. And in particular, many people have composed haikus about SETI. And I think thousands of people have sent us haikus about SETI. But don't worry, I'm not going to read you thousands of haiku. I just want to read you a couple. So a couple of SETI haikus. So the first one is Paula Cook at Duke University. Searching for life, answers are revealed about ourselves. And then this is the last slide. Dan Seidner, 1 million Earthlings, bounded by optimism, leave their PCs on. So thank you very much.
Great, Dan. Thanks. So we have time for questions. Go ahead.
So now that we have the technology for distributed computing, how is the availability of distributing computing power evolving over time? Is it steadily increasing? Are we looking at a ceiling?
So that's one of the nice things about computing is that it's like having millions of system administrators out there. Kind of, if something goes wrong with their computer, they fix it up for us, and then they buy a new computer every few years. That's even better, because it used to be we'd have to build a new machine every few years. So that's a lot of work and expensive, although I kind of like that kind of stuff. And we still do that because a lot of the data that we analyze, the data is just pouring out at many terabits per second, and we can't analyze it by sending it out over the net. So we can do a kind of crude job of analyzing it at the observatory. So we build instruments. But some of the data is small enough data volume, data rates that we can send it out of the internet. And so the volunteers they're growing at the same rate that Moore's Law growing. I think thanks to people like you that are upgrading their computer all the time, it grows exponentially on that same track. Yeah.
So what's the protocol when there is a
good question. Okay, yeah. So what if we find it? Well, so the protocol that we've signed on to and other groups, there are many groups doing it. I just talked about our Berkeley group. So that before we make a big announcement, what we want to do is first make sure that we've got something we think is pretty interesting. And so the protocol says that the first thing you do is you ask a different group with a different telescope, different people, different software, different instrumentation to look at it as well. And because it might be a graduate student playing a prank on us or something like that. So a bug in our software or something like that. So, but if they can see it too, and then you can do interferometry experiments to measure the distance to the source, and you can make sure it's not a satellite or something that's local, so you know it's not radio pollution. And then I think we'll have enough confidence to say that we found something interesting. We won't know if we found ET at that point, likely. So at that point, we'll probably say that, hey, there's something really interesting in the sky. At that point, you make all the information public, the coordinates, the frequency bands, any data that you've got on the thing, and you make it available on the web. And what you hope at that point, and you probably say something like, there's a really interesting radio signal, here's what we know about it. Might be ET, might be some new astrophysical phenomena. You might know when Jocelyn Bell made a discovery of these regularly pulsating things, they didn't know what they were. They called them LGM1, LGM2, Little Green Man 1, Little Green Man 2. Turned out to be she had discovered pulsars. Her thesis advisor that told us her not to do that got the Nobel Prize. She did not, but she should have. She did all the work. Anyway, so I understand she's going to be speaking here in a month or so? In April, yeah. So that'll be, you should ask her to talk about that. Anyway, so it could be something like that, some new phenomena that was not anticipated, or it might be ET. So what we hope, as soon as we make the information public, that a lot of people start looking at it, try to figure out what it is. And we're trying to do something, organize it so that all the nations share information. And of course, we won't be able to track it for very long. Other countries will have to come into play as the Earth spins around. That's the protocol. Yeah?
I guess it also kind of relates to protocol. And I was thinking about it earlier when you were talking about the various different sciences that this project can touch on. And it seems that it can also touch on some history because, in looking at history, it seems that usually when civilizations meet one another, one ends up exploiting the other. So this intel gathering seems like to an advantage to us. But if you're in circles where people really believe we're going to find ET, what do they say about what we should do to maybe minimize them finding us?
So there's this thing there where some people advocate transmitting messages out. I showed you an example of one of these messages that was sent out in the 70s. And that's called METI, Messages to Extraterrestrials. Our SETI is passive. We're just listening for stuff. But some people, and they're in a small minority of astronomers, but some people think it's a good idea to transmit to nearby stars or deliberate messages out there. Of course, Earthlings are transmitting all the time, but not deliberately. So this thing called METI, is, I think it's not a good idea. Most people think it's not a good idea because of just what you alerted, is that when advanced civilizations come in contact with less advanced civilizations, it's usually not good for the less advanced civilization. And so we don't know if they're going to come and eat us or whether they're just going to give us a lot of information or take all our minerals away. We have no idea. So I grew up in the 60s, and I'd like to think that the universe is a peaceful place, and we're all hippies and flower children, and but maybe that's not the case, and maybe that's naive, and so I don't know. So I think transmitting is not a good idea, but even receiving has dangers. Like if we learn a lot of fancy technology and science, and the militaries of the world get a hold of that stuff. As you know, technology can be used for good or bad, and so I think we do have to be really careful about this sort of thing. But I especially think we should not be transmitting, deliberately transmitting.
Question?
Some people are convinced that there is already communication and there's already been people visiting us from a variety of sources. The internet makes that kind of fact-finding very easy. What's your approach to talk to people like that? And where would you direct them, or where would you direct people in education and outreach?
That's a very difficult problem. There are a huge number of people, as you know, that think UFOs have landed, and they're talking to President Trump, and he gets to read all that information, but we don't know. And they talk about alien autopsies, and a lot of people believe that stuff. And I've gone to some UFO meetings, and I've tried to convince them that this stuff has nothing to do with ET. But I'm usually not successful. So what I talk about is kind of things that have people, whenever there are some serious scientists that go and pursue these various phenomena. And a lot of it, you probably know, is real stuff. Like we get calls all the time when the space station's going overhead. You see this bright thing going across the sky. And people call up and say, it's a UFO, it's a UFO. And sometimes it's embellished, it had windows or streaking or something like that. And when the shuttle was was around and it was docking, we used to get a lot of calls, and people call with this aurora, all kinds of kind of real natural phenomena or human phenomena. It gets kind of overinterpreted. And then I think some of it has to do with people's imaginations. And we know that because before Jules Verne, nobody saw flying saucers. But when Jules Verne wrote about flying saucers, everybody started flying. Before Jules Verne, people saw angels. And then after Jules Verne wrote about flying saucers, people started seeing. And people they usually see what's in the movies, so the saucers usually or whatever look like what happened in that year's movie. So we know, I don't think it's deliberate, but people dream about it or they imagine stuff that's in the popular press. And some of it's deliberate hoaxes, like von Däniken and stuff. They make a lot of money by saying that the pyramids were built by aliens and stuff like that. So I think it's a combination of all these different phenomena. And I talk to people about it, and I'm usually not able to convince people that these things have nothing to do with ET, even though I'm optimistic about life in the universe. I think, so I don't know exactly how to talk to people, but I'd be interested if you got a good way to convince people that UFOs are not related to ET.
More of a lighthearted question. What's your favorite answer to the Fermi paradox? The one that you hold most true.
Okay, so I think most of you know about the Fermi paradox, but just to explain your question. So Enrico Fermi, who was here, I think underneath your football stadium, had a lab here. Oh, University of Chicago. Okay, I apologize. Okay. So anyway, he was in the local neighborhood. He, at lunch, he was talking to a bunch of other famous physicists and just casually said this funny remark about where are they? If ET's so advanced, if they're, we talked about civilizations billions of years ahead of us, Earth is 5 billion years old, some stars are 10 billion years old. So if there's these super advanced civilizations, why aren't they coming to land and meet Trump and shake his hand? And why aren't they here? And you can kind of make a quick calculation that shows that if you wanted to do this, you could build self-replicating probes and you could conquer the galaxy. You could have billions of probes and they'd be all over the galaxy. And you could do that. I mean, we don't know how to do that, but any civilization worth its salt could probably do that. And we don't see stuff like that. And so people have thought about that. And some, I don't know the answer, but there's lots of different scenarios. So one possibility that I'm not happy with is maybe maybe space travel is hard. I think, right now it's hard for us, but I can't imagine in 1,000 or 1,000,000 years it's going to be hard for us. But I think the answer is probably not technological or not related to fundamental physics. I suspect it's more of a motivation question. So right now, Earthlings are kind of in this exponential growth phase. We talk about how fast we can grow and pollute more and more and use more and more energy. But my guess is that advanced civilizations don't grow exponentially. All other species we know of have this kind of S curve, and that eventually we'll get tired of this exponential phase and we'll turn into poets and do literature and maybe we'll map out the universe or something. But maybe we won't be interested in conquering the galaxy. Maybe we'll get on the galactic internet and we'll learn about all the civilizations that are out there, and we'll learn that there are laws that you can't just go pollute the galaxy with probes and stuff like that. Another possibility is that they already know about us, that we're in their catalog, but we're kind of like ants to them. We don't try to talk to ants. We study them a little bit. Or maybe there's the prime directive, if you watch Star Trek, that advanced civilizations are not allowed to go messing around with primitive people like us. Maybe when we stop killing each other, they'll come shake our hands or something. So there's lots of different scenarios, but I think it's more about sort of anthropology and motivation than. My guess is that it's not some kind of limit in physics or technology. There's a good book about this, about 50 solutions to the Fermi paradox by Zuckerberg that I refer you to. But the answer is we really don't know. And it is an interesting question. And it came from Chicago.
Dan, I have a question. Could you tell us a little bit about this laser-powered sort of cameras that are I guess presumably going to planet. This is a Russian-supported sort of a
so the guy who's funding our project, Yuri Milner, he has recently announced, we were the very first SETI project, so he gave these breakthrough prizes which you might have heard about, these $3 million projects, kind of like the Nobel Prize, except with movie stars. And then he started funding science projects, and we were the guinea pig science project, the LISTEN thing. And the next one that he announced is called Starshot. I think this is what you're asking about. And the idea is we want to send a spacecraft to Alpha Centauri at 20% the speed of light, which is a hard thing to do. And the way you do that, or at least the planning, and he's going to spend about $100 million, which is not nearly enough, but he knows that it's going to be sort of to learn how we might do that. And the way we think to do that is to build an extremely lightweight spacecraft that's a sail. It's about 1 gram. It's 4 meters by 4 meters. And you propel it with a laser on Earth. Originally it was going to be in space, but they thought a Russian billionaire with a laser in space is not a good idea. So they're going to have this 50 gigawatt laser on Earth that hits this sail for 2 minutes, because in 2 minutes it accelerates at 50,000 Gs and gets up to 20% the speed of light. And by that time it's so far away the laser is way bigger than the sail. And then it just coasts for 20 years to Alpha Centauri. And we think it'll be nice to have a little camera on that, so when you get there you can take a picture and send it back. So anyway, there's a lot of difficulties, as you might imagine, constructing a sail that's 4 meters across that weighs 1 gram. It's got to be really reflective, like 99.9999, because if you put a 50 gigawatt laser on something that absorbs a little bit of light, it gets really hot, and then the sail evaporates. You've also got to keep it very level, because if the light hits more on this side than that side, then it starts spinning around. And there are a lot of complicated problems that we don't know how to solve, but people are starting to think about it. I think it's 100 years away, but it's kind of a fun project.
Any other burning questions? Okay. All right, well, let's thank the speaker. And